colleagues at DePaul and Purdue. For the last few years, I've been looking at relaxed memory models, and so what is the subject? So when one is looking at concurrency in a uniprocessor world, life is relatively simple. Time is global, which means the sense in which I'm using that word is that interleaving semantics is a pretty decent account of what is going on. And I'll look at more precise ways of saying that in a minute. But then when one moves to the current world, even our phones or machines, we live in a multiprocessor world. So now suddenly what we are really in is some kind of distributed system. So the linear view of time is no longer accurate. And reasoning becomes a little bit more involved. And I think this has given relaxed memory models a bad name. And what I've spent the last few years looking at is to say whether this view that they are complex is really justified. So this is, so we started with our ESOP paper where we looked at the Java memory model. The Java memory model is presented axiomatically. What we did was we turned our traditional operational semantics tools on it. Our ESOP 2010 paper tells us how to view the Java memory model operationally. Then we tried to see how much we can push traditional techniques to understand relaxed memory models. So in our Fossack's paper, what we did was we showed that our old, well-known Brooks-style trace semantics for shared memory, single processor computing can indeed be pushed to a certain class of relaxed memory models. Okay. And since then, what we've been trying to do is we've been trying to understand how to reason with programs which are written in this setting. So that's really what I want to talk about today. But before I do that, if you will permit me, I want to reminisce for a couple of minutes. So I joined Samson in 1991 August. I was there till 1993. And two things have lasted since then. So the first is I met my wife in 1991 September, and we got married in 1992 August, and we are still married, okay? So something was right. And the second thing is that when I left Imperial, Samson bought me this t-shirt. So I still have it. Okay. And the other thing I wanted to, so when I grew up in India, and when I was in high school, they'd make us narrate this Sanskrit sloka. Okay? And my parents thought it was more important for me to know math than Sanskrit, so of course I never knew what it meant. But now, with the world and Google and everything, one can find this. So it turns out to be a kind of a salutation to one's guru, and since Prakash and Samson are here, this is a good time to do it. Okay. So of course we start off with a mandatory invocation of the Trinity in our mind. But then it goes on like this, right? It says, he creates, sustains knowledge and destroys the weeds of ignorance, and I salute the Guru. There we go. I salute the Guru.
Is one of us Vishnu and the other one Shiva?
No. So when I discovered this, I found this, I started smiling, but I also found this, it freed me. Because then I realized that anytime I got a bad referee report, the ignorance which I was accused of was not my fault, it's their fault. So, anyway, so let me go on to my talk. If you find ignorance, you know whom to blame. It's not me. Okay? So, what I want to do is today I want to talk about linearizability. Right? So let's remember what linearizability is for sequential programs. It gives us a really good idea about what is an interface of a concurrent object, right? And when we think about linearizability, as we will see, there is the implicit causality, and the implicit causality is via absence of interleavings, and the definition of linearizability really relies on this. Right? And so what I want to do in this talk mostly is to talk about what changes we need to make to account for relaxed memory, weak memory. Okay? And the punchline is basically going to be that we have got to take explicit causality seriously. And in the relaxed memory world, this is called happens before. Okay? But in order to sort of put this all together, I'm going to do this talk mostly with examples and diagrams. So let's go back to a Spinlock, okay? So this is sort of, if you want to think of it, it's an old OS lock. So what are we doing? We have a release method and an acquire method. We are implementing it with atomic compare and set instruction. So basically, what does that say? Well, if my current state of V is 0, change it to 1, right? So that's what it says. So if you think of the trace of a release, this is the kind of notation I'm going to be using. It's reminiscent of games, process algebras, right? I'm looking at it from the lock's perspective, so I'm thinking of it as an input to the lock. So if I call the release method, I have some actions to stand for the memory actions. WR will stand for write. So, and then the bang tells me I'm returning from the release, right? And then similarly, we have acquire. So I have a call to an acquire, and I'm going to write unsuccessful CAS instructions as reads. So I have I'm unsuccessful with the CAS for a bit. The state was 1, so I read a 1. Then I succeed, and the successful CAS is written as I've shown you there, and then we return from the acquire. Okay, so that's how a trace of an acquire looks. And of course, we can have these, and I'm dropping the thread identifiers. So this is kind of the scale here. We can have interleavings of these methods. So here is a successful interleaving. So I call the acquire. I have an unsuccessful compare and set. It can't succeed yet, right? So then I have a call to a release, which writes 0 into the variable. So now acquire can succeed. So which is why I have a successful compare and set, which you see there. And then I return from the acquire and I return from the release. Okay? That's a possible interleaving. And of course I have a impossible interleaving where clearly I cannot have what's the intuition, right? I just want, we know that the acquire can't return before the release. Before the release goes through sum anyway. So that's an impossible interleaving. We can't have acquire. In this case, I can't have the return from the acquire, the bang action, before the query action to the release. Yeah? So if you want to think about it, what are we saying really? If you look only at I/O actions, the input-output actions, the constraint we are talking about is that the call to the release must precede the return from the acquire. This is the causality we expect, right? And I'm going to be just, even though I'm really talking about sets of traces, I'm going to compress my presentation of the sets of traces just by thinking of what constraints on the interleavings I have. So what do I have here? I have a release happening and I have an acquire happening, and the interleavings are constrained by the fact that the call to the release must happen before the return from the acquire. So that tells me what interleavings are permitted in the system, right? Okay, and just to sort of finish off the story. So what is the interface of a lock? So one might say, if one stays in the old world, one might say, okay, it's a set of traces, just of input and output actions, that is calls and returns for us here so far. And the constraint we have is that the calls and return, the call to the release must, there are these sort of cross-method dependencies, which is that the call to the release must be before the return from the acquire. And of course, the lock itself, since the thread which calls the lock has to maintain thread order, we have some dependencies coming from the fact that the call to the A method has to happen before the return from the method. So we have a call to the release happen before the return from the release and so on. Right? So that's how it looks. That's my interface of a lock. Okay? So this is the old view about the lock. But let's, so how does the client play into this? So the client imposes some extra order, right? So let's think of multiple calls from a single thread. So these blue edges there tell us ordering relationships which the client imposes. And one recognizes that these ordering relationships are kind of different because you have edges going from the bank to the query, right? Which is because the client has called and returned from the acquire before calling the release. Okay, so that's what happens. And of course, you can have what these arrows are doing is they're constraining interleavings. And if you have more arrows, you have a smaller set. If you're fully constrained, you're done. You get a So that's the world as we understand it, right? The Spinlock. So this is what the interface of a Spinlock is. Now I'm going to try to argue that this interface is not sufficient for composition. Okay, so this is so let's use the Spinlock in an example. Let's say we are building a one-place buffer, right? So what are we doing? So I have I'm implementing this buffer. It just has one slot. It's going to have there's the full lock, which basically is is checking for the buffer being full, and there's an empty lock, which is checking for the buffer being empty, and these two locks are independent, right? Of course, each of those locks has to satisfy the interface of the lock. So we have our dependencies from the acquires to their respective releases, right? So we have the acquire of the full lock to the return of the release of the full lock, from the call to the acquire of the empty lock to the return from the release of the empty lock, right? So that's what's happening. And of course, again, the client can create dependencies which are going across. Now let's think of a full interaction of the buffer, which is initially empty, right? So what happens? This is the kind of dependency we expect. What's happening? We're going to, based on the interaction we are thinking about, is we're going to put 42 into this buffer. Then we're going to get, we expect to get 42 out of the buffer when we do a get. Then we put 27 into the buffer. Then we expect to get 27 out of the buffer. This is what we expect, right? Okay. And now let us see how this looks from the buffer's perspective, right? Of course, from the buffer's perspective, when the buffer is using the lock, we're going to see a flip of polarities, right? So from the buffer's perspective, what appears as an outgoing call action to the lock turns into a query. Okay, so there's the perspective switch which one has to track. But here's the full trace, right? Here's the full trace. What's happening? So let's walk through the left a little bit. So the buffer is empty initially. So when we're trying to stick 42 into the buffer, we acquire the empty lock, we return from the empty lock, we write 42. I'm still walking down the left there, which means I can release the full. So what that means is that when I do the get here, I have the correct dependency I need. Okay, so I'm allowed to return from acquiring the full, so I get 42. All right, and I'm just repeating this once again, just to get an example. So I expect if I put 27 in, then I expect to get 27 out. Okay, so this is what I expect. All right, but now let's focus on this. Let's focus just on the memory actions involved here. Okay, so what's happening here? So if you look at the memory actions, I have a write of 42 into this variable, shared variable, and there's a release from by the full lock, and then I have an acquire to the full lock, and I expect to see 42. And here, when I do 27, again I have the same thing. I am releasing the full lock and I'm acquiring. Now the question is, right? Is it possible for me at the second read to get an old value which is a stale value, or do I have to get only 27, right? And in the old view of memory, where time is global and memory is centralized, the only thing you can get is 42. Sorry, the only thing you can get is 27, right? But in the Java memory model, with this program, in fact, you can get a stale value, right? Even though, so what I'm trying to build up here is basically saying that there is even though the interleaving is constrained this way, right? So there's no other, yet we are able to see stale values. And this is not just about the Java memory model. There are similar examples in all of the memory models, if not the same, okay? Right? So what's the problem here? The problem here is that the lock tells us how to constrain interleavings, but it's not telling us about the memory effects that it creates. Okay? So the old interface of locks, which tells us about how it constrains interleaving, just does not have enough information to compositionally build up and use for a client in the context of a client such as the buffer. Okay, so this is the This is what this is the message. Okay, this particular program can be fixed in other ways, but what we really need to do is we need to accept that the lock also provides happens before, which is the relaxed memory way of saying it provides genuine causality. Okay, so here in this case, I'm going to trace this a little bit with happens before in a minute. Okay, so what are we doing in this talk, in this paper, right? So we're going to say we're not going to take interleaving that seriously. We're going to really focus on on adding causality information to our interfaces. Okay, so this is what we're going to try to do. And so the plan for the rest of the talk is like this. I'll just walk through our old notions of connectedness. I'll talk a little bit about happens before. I'll tell you a little bit about the results we have. Okay, and then if Prakash lets me, I will speculate about compositionality. Okay, so that's the plan. Okay, so old stuff, right? So we have sequential consistency. What do we want? We want our methods to be atomic, right? So what does that mean? You pick a trace, like of the kind we have seen, sequences of input and output actions. Then what we want is, we want a sequential spec, which means that the outputs and outputs are lined up next to the corresponding inputs. So methods kind of appear atomic, right? And the constraint we want to maintain is that we project down to individual threads both the implementation trace and the spec trace agree. Okay, so this is what we want. Okay. Now, what is it's serializability is probably a better word for it. Yeah. What does linearizability do? Linearizability demands what we see there for serializability. It furthermore says that the two sides must agree on the order of non-overlapping calls. Okay? Okay. So what does that mean? So let's look at an example here. Right. So here, let us say we have a call F and a return F and a call G and a return G. Let's say the call F and the call G are happening in different threads. Serializability would permit me to swap them around. Okay. Whereas linearizability says, no. If in my arbitrary scheduled trace I see f end before G is invoked, then I have to maintain that order. Okay, so that's your basic example, which distinguishes serializability and linearizability. And what one gains for this is a little bit of compositionality, which I'm going to describe in a minute. Okay, but now how are we going to change this world? We're going to change this world by thinking just of happens before relationships. I'm not going to show you details, but I want to just give you a high-level view of this. So the first thing I want to point out to you that what I'm describing to you is not specific, to a specific memory model. Okay, so for example, what I'm describing to you works for traditional sequential consistency, which I've called strong here. It works for total store order, which is basically the memory model used in the x86. It works with the JMM, the Java memory model. Okay, and but I'm just going to be very abstract. I'm not going to tell you too many details about these things, right? But what's the main innovation we are adding to specifications? The innovation we are adding is we are permitting specifications to incorporate happens before relationships from the calls of methods to returns of different methods. And such memory annotations are already part of the spec of concurrent libraries. So for example, if you go and read the Java implementation for stack, what they're going to tell you is that if you have a push method and a pop method, then the return of the pop method happens after the call to the corresponding push method. So this is the kind of documentation you see in the Java memory model. Okay. So, all right. So that's so we are going to allow such information to be part of our specifications, and that is the the arrows which you're seeing between queries and banks, right? And of course, to keep things neatly compositional, we also want to make assumptions on the environment. Okay. So what are we doing there? Those are the blue arrows. Okay. So that's basically the assumptions which the library is making on how the environment actions are ordered. Okay, so those are those are the ingredients of our specification, and these are the only new ingredients beyond what you already see with over hurdy and wing, for example. Okay? And these things can be generated from the operational semantics. I mean, it's the details are not important. I mean, what I've shown you there is what works with the Java memory model. Okay? And it's like in some memory models it's easy to generate this. So for example, for sequential consistency, one can generate it easily. One has to work much harder for models which are operationally based, like total store ordering or processor store ordering, but it's possible. Okay? I'm not going to bother you with the details. Okay? But now let's return to the one place buffer. This is the scenario we had, and now the question we were asking was, well, hey, is it possible for me to read 42 from the read 42 at that place, which is a scale value? Okay? And in this case, it turns out it's not possible. Okay, it's not possible if the blue arrow is there. It happens before. So what does that mean? So why is it not possible? It's not possible because, okay, let's see when we come to the the shaded action there. So what are the writes it potentially sees? The writes it potentially sees are the 42 and the 27. But now the two writes, the writes to 42 and the writes to 27, are ordered in the happens before relationship. So now the 27 really is obscures the 42. Okay, so this is a genuine hard ordering which one sees here. Okay, so in this case it's not possible to see it with happens before, and that, of course, that's the essence of why now a lock spec with the happens before ordering can be used to program the buffer, and it behaves in the way we expect it to behave. But anyway, so that's why it helps. Okay, but now let's return to our formal definitions. Just again thinking high level and schematically. So what is linearizability? So we have a set of traces. Your sigma on the left is your set of implementation traces. Your phi on the right is your spec traces, right? And what are we saying? Well, for every implementation trace, we need a spec trace. And they agree on the same IO action, so the calls and returns. They preserve third ordering, okay? So that's that. And if there is a return on the implementation side, if a return of a function precedes the call to a different function, then that has to be respected in the spec side. So this is a hard constraint, an arbitrary scheduling constraint which is reflected here. Okay. Now, how do we do here? So I've just flipped to our definition, right? So we are not going to impose this hard constraint. What are we doing here? So again, we have the same scenario. We have some implementation traces and some specification traces. They have to agree on the IO actions. And now what do we demand from our implementation? What we demand is that the implementation enforces all that happens before that the specification wants. Okay, it may impose more, but it imposes everything that the specification wants. Okay, and we have to make sure that the extra stuff it has does not contradict the specification, and we have to make sure that the environment assumptions are preserved. Okay, so this is how our new definition looks. So the thing with the difference here is basically that there's now a happens before requirement in the specification, and the implementation actually realizes this order. Okay, so that's what we do. Okay, so now let's think about how the refinement theorems look. So this is all how. So we have a client and a library. So how a nice way to formalize this is by Filipovich, O'Hearn, Renetsky, and Yang. What do? They say, well, if sigma, which is an implementation, implements the specification in the linearizability sense phi, then in fact in any context you can replace sigma by phi in the sense of observational refinement. Okay, and this theorem is extended to a specific memory model, which is the total store ordering model in this paper of Burkhardt, Gotsman, Musuti, and Young. So here what do they say? Well, if you have an implementation which implements a specification, then you can operationally replace the spec by the implementation. Okay, so that's what they do for a specific memory model. What have we done? What we have done is we say, okay, pick a spec for the library. Okay, and let's assume that with this spec for your library, you're able to prove some property for your client, okay? And the use of tensor here is it's intended to be suggestive. It looks like the tensor you might think it is, but in a with push-down context, okay? Then what we are saying is basically, yeah, in fact, you can in fact run the library with the client, and the client is going to get their properties. And this is true parametrically, essentially over the memory models, and what we identified basically a bunch of properties on the relationships. So we are able to prove this for a few memory models generally. Okay? And we get, in some special cases where you can make some extra assumptions about your programs, we show that in fact you can go back and use old linearizability itself. Okay? So that's the story. Now let me speculate. Okay? So one interesting bit about linearizability, and in fact this was Hurley and Wing's important motivation, is they want to say, oh, let's say we have two objects. Okay? So I have P1 and P2. They're disjoint, so they're not. They don't have any state in common, right? And they implement their interfaces. When does just putting them side by side disjointly? When does that implement the tensor, right? And what Hurley and Wing do in their paper is they show serializability in fact does not satisfy this property. Okay, so there is we don't need to look at the details. So here we have the example is based on two queues. One of them is going to be called A, one of them is going to be called B. And here you have two columns intended to suggest two different threads. And what you can see is that when you go from the left to the right, you are reordering actions between threads. I moved the 27 before, and serializability permits this. So I do this on QA, I do this on QB, and suddenly I put QA and QB together, boom, it doesn't work anymore. Okay, so serializability does not compose, even for disjoint objects, which don't talk to each other, right? And Hurley and Wing identified this. The way they fix it is to say, oh, it's because, in fact, we broke this non-overlapping order, right? The non-overlapping order being here, so the thread on the left finished some queue operation before the thread on the right invoked it. And this is an arbitrary scheduling, right? Totally arbitrary scheduling. But in the Hurley-Wing world, you have to preserve this order. Okay? And, right, so, and this is the crucial point, basically, that, that we are not able to interchange independent actions in independent threads, and that's essential to Hurley-Wing, right? And but of course, if my interface is saturated under all these under all the appropriate permutations, then it's going to be fine. Okay. So what we permit, in fact, is we say in this particular example, we say, oh, there's no intrinsic order between the actions in these two threads, so we're going to permit it. Okay, we're going to permit it. And, just because implicitly our definition is kind of performing disclosure at some level, right? So that's how it works here, okay? And so I think the case we are building is that if there is no happens before edge, if it's not part of the interface, then a spec which constrains method invocations from different threads is fundamentally unreasonable. In a world which is, which is kind of distributed, okay, right? So in the world with a single processor, interleaving gives you accidental orders, and that's crucial to how linearizability works. And it gives you really elegant ways to establish compositionality, right? Now, in our world, we are suggesting a different route to compositionality. We are saying, oh, just bad accidental order in specs. So take specs, close it under, intuitively, close it under the orderings which are not specified. But of course, that means that, there's a downside to this viewpoint, which is that the specs we are used to writing, stacks, without explicit orders, are not going to look like stacks. Whereas bags, are naturally closed. So from that perspective, I think it's, there is some counterintuitive stuff going on there. But on the other hand, we know that data structures like stacks have fundamental complexity lower bounds when you implement it in a concurrent world. Okay, so there is, roughly speaking, the amount of conflict you have in implementing a stack has to be omega n in the number of threads, right? So if one looks at the modern literature, there is a tendency, there's an intention to explore data structures which do not have these fundamental constraints. But this is speculative. Thank you.
So does this idea about getting compositionality in this way by sort of going to a more permissive data structure, I mean, how might this reflect in the way that you program?
It makes it simpler to program. So it's so there are really, for example, for bags, there are quite beautiful programs which basically reduce contention, so it's already been observed.
It's a little bit reminiscent of the sort of multi-set programming and the sort of chemical abstract machine type.
Oh, I see. Yeah.
No, you see some analogy there.
Oh, no, that is true. I never thought of it that way. That is true.
So being the source of knowledge in your life?
And ignorance.
I was wondering if you had thought about the role of epistemic logic in these things. So you may remember Kim Taylor and I developed an epistemic logic particularly adapted to these kinds of causal systems. And many of the arguments that you gave remind me of proofs that Kim and Carol Crispo did for showing impossibility results.
That ignorance I can't blame you for. Yes, I guess. No, I didn't.
There does seem to be an epistemic character lurking under the surface to some of the things you're doing.
No, I should read this. Yes. No, I haven't thought about it.
Yeah, it's too tell you things.
Yeah.